directional selection, that means that there should also be a stabilizing selection model. And under stabilizing selection, both alleles are valuable. Individuals that only have one allele type would have lower fitnesses than individuals that are heterozygous and have both allele types. So let's change our model here, and we're going to give the two homozygous individuals the lowest fitness, and the homozygous A2, we're going to give the two homozygous individuals here the lowest fitness, and the heterozygous individual will have a 1 representing the highest fitness possible. I'm going to start the allele frequency off at 0.5. Think in your head, well, what should happen to this allele frequency? Should the allele frequencies change? If they do, should I get to fixation? What should happen? Okay, and the way I've set this up, the allele frequency is going to hover right around 50%. Okay. As an aside, why is it bouncing around like that? It's because my population is not infinitely large. You're seeing sampling error in action. Okay. See that coming over there? All right, what if I started the allele frequency off someplace else? What if I increased the frequency of the A1 allele at the expense of the A2 allele? Okay? That would mean here, I'm going to start it off at an 80% A1. We'll start it here. What's going to happen? Right? It comes back to 50% again. What if I started at 0.1? Comes back to 50% again. This is a weird situation for natural selection. When we've done natural selection before, we always talked about natural selection working against alleles to remove them from populations. Right? In favor of the best fit genotype. Well, in this case, selection is working to keep both alleles in the population. And it's actually working to keep both alleles at the highest frequency that it can, which is 50% A1 and 50% A2. Okay? Now, this seems like an unusual situation, but it's actually not so uncommon. This particular condition is called heterozygous advantage. And it occurs wherever both alleles together confer an advantage that neither of the homozygotes have. Okay? Best studied example is sickle-cell anemia. So let's set these genotypes up by presenting the alleles first. Let's say that A1 is the wild-type allele. That's the most common allele in the population. And the A2 allele is the sickle-cell allele. And this allele causes sickling of blood cells. It causes a change in the binding affinity of hemoglobin for oxygen. That would give us 3 genotypes. This one, and this one. This individual has sickle-cell anemia. They have 2 copies of the sickle-cell allele. They have sickle-cell anemia. This condition in today's world requires blood transfusions because the blood cells have a hard time binding oxygen. They tend to stick, the hemoglobin tends to stick to each other, and you get these plaques forming and not a lot of oxygen is carried. Prior to transfusions in modern medicine, the expectation was individuals with sickle cell anemia, when they reached about 8 or 10 years old, they were going to die because the body gets larger, you need to carry more oxygen, but on the other hand, you're having trouble because you can't bind the oxygen efficiently. Okay? Now, in parts of the world that have malaria, it turns out that these individuals are susceptible to malaria. And malaria is a big killer. It's in the top 5 pathogen-related deaths in the world. I think heart disease is the #1 killer overall, but just in the pathogens, malaria is one of the big killers. It kills a lot of people every year in parts of the world where that malaria plasmodium exists. The malaria plasmodium needs to be able to grab onto red blood cells, and it appears to do so through the receptor that the sickle cell is involved with. So individuals that have the kind of wild type receptor are susceptible, but these individuals, because of the difference in receptors, they don't get malaria. They also don't get sickle cell. They're carriers for it. You can notice the cells sickling at low oxygen partial pressures. So in parts of the world like Mexico City or Denver, Colorado, you would notice the sickling of cells under the microscope. But as long as individuals aren't engaged in some crazy amount of physical activity, these individuals would be fine, and you couldn't tell them apart from wild type. As an aside, multiple years ago, those of you that are Pittsburgh fans know the story of I think he was a tight end, I think he was a tight end. Can't think of his name. He played in a playoff game in Denver, Colorado, and turns out he was heterozygous for sickle-cell anemia. He's working at low oxygen tensions, incredible amounts of physical activity, right? Professional football. He ended up in the hospital. I think he lost his spleen and a kidney, all kinds of nasty stuff, because the oxygen wasn't enough of it in his circulatory system to meet the demands of those organs, and stuff started to shut down. Okay? But the way this typically works at sea level or under moderate physical activity in Denver, Colorado, individuals that have the A2A2, sickle cell anemia, individuals homozygous A1 in parts of the world with the plasmodium, malaria, and the heterozygote doesn't suffer any problem due to either. These individuals have a lower fitness because of susceptibility to malaria. These have a lower fitness because of susceptibility to sickle cell, and these individuals have the highest fitness. Natural selection works to keep both alleles in the population, even though each of these alleles by itself are pretty lousy. It's only when they're together that things are good. Is that okay? All right, as I say, there are lots of examples of that. I'll probably include one of those on your take-home exam. Okay? That leaves us with one other option here, and that's a type of selection that occurs when you select for the extremes. That would be disruptional selection, and this would be heterozygous disadvantage. Okay, heterozygous disadvantage. All right. Let's see how that would work. Well, to get this to work properly, I need to change the fitnesses here so that the extreme fitnesses end up with the highest fitness. Let's start the allele frequency off at some value here, 0.1. And very quickly we lost the allele from the population. If I started the allele frequency off at 0.6, what would this look like? Same thing. In heterozygous disadvantage, through disruptional selection, natural selection doesn't really like the heterozygote. So whichever allele is more common in the population, that's the allele that will be selected for. I started out with a higher proportion of the higher proportion of the A1 allele, that's the light blue, and it went to fixation because it's the more common allele. Natural selection will run with it. Okay? All right, so we've got natural selection operating here through this kind of directional, stabilizing, or disruptional selection. Directional, it matters if it's dominant or recessive, and in both stabilizing and disruptional, it matters whether the heterozygote has the lower or higher fitness. Okay? All right. So I'll see you on the other side of resetting things.